today.
Recording in progress.
Now, okay. So today we are going to talk about this paper, causal interpretation of stochastic differential equations. Well, if we have non-temporal data, we usually try to model this data in terms of causality with these structural equation models, which if you're not familiar with, I will quickly talk about somewhere in this presentation. And then using those structural equation models, there is this notion of intervention. And so we use this notion of intervention to talk about causality between these different random variables that are non-temporal and that we observe. But if we have time, so if our variables also, our data is also temporal, then the question is how we can infer causality in that setting. So in this setting, first, we should decide how we want to model our data. And one way to do that is using stochastic differential equations, or for short, SDEs. So in this paper, SDEs are the way to go. So that's the model that they consider. And then they talk about how we can define intervention for SDEs. And so when we have interventions, then we can talk about causality between these different time series that we are observing. So just to have like a good idea of what the setting is here, first we have these omega F, Ft, and P, which is a filtered probability space. And what does that mean? So it means that omega F and P is just the normal probability space that we usually define. And then for every T, Ft will be a sub sigma algebra of the main sigma algebra F. And also for any S that's less than T, less than or equal to T, Fs is a subset of Ft. So here we have this increasing sub-sigma algebra, increasing sequence of sub-sigma algebras. So that's the filter probability space. Now, Z, which is called our driving variable here, is a d-dimensional semi-martingale. Now you might ask what the definition of semi-martingale is. I'm not going to give the definition, but I'm just going to give some examples of the semi-martingales that we will use throughout this talk. So the examples include the Brownian motion, which is like maybe one of the most famous ones. The Ito processes. And what is an Ito process? It's a process that satisfies a differential equation like this. Dx is something like sigma dw plus mu dt, where this w, and you can say dxt is sigma dwt plus mu dt, where this w here is a Brownian motion, and sigma and mu are adopted processes, meaning that for each t, sigma of t is ft measurable. And also mu of t is ft measurable. So that's one example, one other example of a semi-martingale. And then we have Levy processes. So anyway, and then we have this mapping A from R, this was RP, RP to M of PD, where M of PD is defined to be the space of real P times D matrices. Now, if anyone is more interested in this notion of stochastic differential equations and integration, this is something that the authors of this paper have proposed to look at, stochastic integration and differential equations by Prater. But anyway, in our setting, how do we define this stochastic differential equation? So in our setting, a stochastic differential equation is defined to be something like this. So a family of equations where for each I from 1 to p, xti is x0i plus the integral from 0 to t of the sum on j from 1 to t of a ij of xs dzsj. So remember that this a for any vector xs in Rp gives us this matrix, this real p times d matrix. So aij is the ijth entry of that matrix, which is a function on Rp. It's a real valued function on Rp. And this is how we define our differential equation for each I. Now, if we want to kind of summarize it, we can here write dxt is a of xt, like the whole matrix A at xt, dzt with initial value or x0. So basically, this is the main setting that we are going to use throughout this talk. Any questions so far?
So that is the same mark.
Yes. Okay. So now that we have the model itself, the stochastic differential equation, let's define this post-intervention SDE. But before that, a notation thing here. So when we say for a vector x in Rp, when we say x minus m for any m from 1 to p, x minus m is the p minus 1 dimensional vector where the mth coordinate of x is removed. So everything else just stays there and the m coordinate is removed, we denote it by x minus. Now it's time for us to define the post-intervention SD. So let m, again, be something from 1 to p, and zeta be a function from r to the p minus 1 to r. Now we want to define the SD arising from this star, which is the original SD, under this intervention. So we want to set our mth coordinate, xtm, to be some function zeta of all the other coordinates, xt minus m, as we suggested in our previous notation. So now this will be the following SDE. It's still SDE, and the remaining p minus 1 coordinates as follows. So yi minus mi will be x0i plus the same thing, integral from 0 to t of this sum. Y is the new name of the variables after the intervention. It's basically y minus m of I is just xi after intervention. So bij ys minus m and dzsj. And this is defined again for every I from 1 to p except for I equals m. And then what is B here? B, like before, is this mapping, but this time it takes a vector of size p minus 1 to a matrix, a real matrix of size p minus 1 times d. And how is this matrix defined? So in this matrix, this S? Yeah. It's just time, but here, because the bounds are 0 and t, we wanted to use a different variable for integration. This is also S. It denotes time. And our Bij is basically defined off of the original mapping A, but here Bij of a vector y will be Aij of y1, y2. Instead of the mth coordinate though, we will write zeta of y, because here we want to replace the mth coordinate, xtm, with this function. So in here, we also replace the mth coordinate with this function. And again, I is not m, and j is from 1 to g. So basically, this is the more precise notation, but what it wants to say is that we replace every XTM on the right-hand side of the original equation, which we are showing with a star, with theta of xt minus m. And yes. And one thing to note here is that here we have this stochastic differential equation. So it's a differential equation. We just call it a stochastic because we have this random structure here. So it becomes a stochastic differential equation also in the original thing that we are showing with star. So in both of these stochastic differential equations, we are never talking about existence or uniqueness of solutions. So the pure mathematical definition doesn't really care about existence or uniqueness. So existence and uniqueness not required. But there are certain cases where we can guarantee existence and uniqueness. For example, we have this when A, the map that took a vector in RP to a real valued matrix, and the map that does the intervention, zeta, are both Lipschitz. So in this case, apparently we can guarantee existence and uniqueness. So that's that. And then just some words for calling all of these stochastic differential equations. So in the original stochastic differential equation, we call it the observational SDE. And if it has a solution, we call the solution the observational process. And then this solution has a distribution, we call that distribution the observational distribution. And similarly, in the SDE that we get after intervention, we call that the post-intervention SDE. The solution to that SDE, if it exists, we call it the post-intervention process, and the distribution of that solution is called the post-intervention distribution. So far, we just had some purely mathematical definitions, and from now on, we want to see if they even make sense in the real world. So the paper has multiple examples, but I thought two of them are like more important. I found them more interesting. So I will show you one example where this definition is natural and is applicable to our setting. And then I will show you one example where it's not applicable. And so I just want to say that so if we decide to use this setting for our causal inference problem, there is no way to test whether or not this is a good setting. So this assumption of this is our model and this is how we define interventions is not testable. We just sometimes decide that this is what we want to do, and then we use the other results that we get. But otherwise, the authors mentioned that there is no way of testing it. But okay, so let's first see this example. So this is something from chemical reactions. Let's say we have two material X and Y, and the concentration of X is shown by capital X and Y by capital Y. And let's say that we have 4 reactions, as you see here. So in the first one, Y is produced with rate A. In the second Y is destroyed and is changed to X basically with rate B1 to Y, where this again shows the concentration, this Y here. And then in the third one, X gets destroyed with the rate B11X. And in the third one, Y gets destroyed with the rate B22Y. And then first, let's model this with a stochastic differential equation, and let's talk about this post-intervention SD afterwards. So they define this lambda xy, which is basically a vector where all these rates are put in that vector, A, B1 to Y, B11X, and B2 to Y. And then also they care about this matrix S, which is called the stoichiometric matrix. Basically shows the number of molecules that are created or destroyed in each of the 4 reactions. So each column corresponds to one of the 4 reactions. And for example, in reaction 1, 0 molecule of X is involved, but 1 molecule of Y is created. In reaction 2, 1 molecule of X is created, 1 molecule of Y is destroyed, and so on. So that's how they get this matrix S. Now, let's see what our model can be here. So the authors mentioned that several models have been proposed for this. and some of them stochastic, some of them determined models, but because, well, we are just setting up SDEs, this is the model that they want to consider. So our model is the following: xt, yt is x0, y0 plus at, the integral from 0 to t of some matrix B, which I will define in a second, xs, ys, ds, plus the integral from 0 to t of this matrix sigma, xs, ys, dws. Now, this ws here is the random part, which is a 4-dimensional Brownian motion. And B is the matrix which involves this rates of these reactions, minus B11, B12, minus B12, and minus B22. And then sigma xy is just defined to be S times the diagonal matrix, where on the diagonal we put the square root of lambda x comma y. So I just want to make sure that we at least agree with this deterministic part, because this is kind of easier to see. And then we have this random part afterwards, which has some arguments. But for this deterministic part, well, remember that these reactions each had a rate. So for example, xt is x0, and then in equation 2, it changes with rate b12 y. So if you look at the first row of this matrix B, B12 will be multiplied by Y. And in equation 3, it is destroyed with rate B11x. So that's why we have this minus B11, which will get multiplied by this x here as the integrand. And also you can check it for YT. So I think the deterministic part somehow makes sense. So anyway, this is the model. And okay, just let me quickly also write this matrix here. So what happens here is that, okay, so just before that, just a quick sanity check here to make sure that this is the form that we want for our SDE, because originally I wrote that x should be d of, sorry, it should be some a of x times dz in the original format. I just want to say that this is exactly what we were expecting. So here, xt yt can be viewed as x0, y0 plus integral of 0t a of xs ys times dzs. It's the same thing that we said before. It's just that a of xs ys can be considered as a matrix where the first column is b xs ys plus 0a. So this is just one column. And then we augmented with this other matrix, sigma xs ys. It's like this matrix here. And then our dzs is just ds, and then this vector dws. So I just want to make sure that we agree that this is the setting that we originally started with, just written, kind of, we have expanded it. So anyway, now I want to do the intervention. One thing that we can do in the real world is to fix the concentration of x or y. Here, let's fix the concentration of y. So basically, what happens if we do that? So the intervention that we are considering is fixing the concentration of yt at a certain level. Let's call it zeta. This is just like a constant. And what happens here is that, so if we look back at these four reactions, sorry. Basically, we are saying that we want to get rid of the first one, want to get rid of the last one, And for the second one, we want to change the rate to B12 zeta. And now the equation for xt, well, yt is always the constant, so the equation for xt will be just x0 plus, if you look at this original equation and compare them, yeah, it will be x0 plus t b12 zeta minus the integral from 0 to t of b11 xs ds plus the integral 0 to t of this two-dimensional matrix, which is the first row of this matrix, because these and these are 0, and for the two other ones, wherever we see y, we just replace it with zeta, and it gets multiplied by dw as tilde, where this is a two-dimensional Brownian motion. So this is a setting where this post-intervention SDE as defined in this paper makes sense. They don't exactly say how, but they say that it is consistent with the mechanical fundamentals of this chemical reactions. Yes, it's somehow possible in the real world to fix this. I mean, they say that we just get rid of these reactions, but my question was also how they make sure that this second reaction, because it changes the concentration of y anyway, maybe they just enter some extra y into the space and somehow keep the concentration the same. So this is one example that I give. Yeah. Now, the second example where it shows this notion sometimes is not applicable, which is example 4.6 of the paper. So in this setting, we want x1 to be a one-dimensional Brownian motion, W, and also let f be a twice continuously differentiable function. And also, so we want to consider a time series with two coordinates. Let's say that the second one, xt2, is just the function f of xt1. Well, here, just by looking at this model, it's very natural that we expect the result of the intervention x1 set to zeta to be this. xt2 is f of this constant, right? If this is the model, this should naturally be the post-intervention model. But now let's see what happens in our setting. So first, we should write our model, basically this one, as a stochastic differential equation to be able to then apply our notion of post-intervention to that SD. So let's do that. This is done using Ito's lemma. So what is Ito's lemma? Ito's lemma. So Ito's lemma says if x satisfies this differential equation, so if x satisfies dx is some function a of x comma t dt plus some function b of x comma t dw t. Here we can also add t. Sorry, where this wt is a Brownian motion. Then for any twice differentiable function, continuously twice differentiable function f, Ito's lemma says we can write df as this. The derivative of f with respect to t plus 1/2 of the second derivative of f with respect to x, b squared dt plus the first derivative of f with respect to x, b dw. And now f of f, so originally in the lemma this can be f of t and x, but in our case it will be f of x because this is our f here, so it's just in terms of x. So how are we going to use it here? So remember that we already know or let me start from here. We already know that xt2 is f of xt1. Now let's work with this f here. So dxt1 is just dw because xt1 was assumed to be a one-dimensional Brownian motion w, so dxt1 is just dw. So if you compare it with this guy here, your A is 0 and your B is 1. Now, let's use Ito's lemma. So df(xt1) will be, so this will be 0, this will be 0 because f is just in terms of x, and then we can use this term. So it will be 1/2 of f double prime of xt1 dt plus then the next term f prime of xt1 dwt. So this term will be 0 because a is 0. This term will be 0 because f is just in terms of x in our case. This term is this term here. And because b was 1. And this term is this term. Because again, b was 1. And now, okay, so originally we defined xt2 to be f of xt1. Now, given the previous line, f of xt1 will be f of x01. We want to integrate the both sides. Plus 1/2 of the integral from 0 to t of f double prime of xs1 ds plus the integral from 0 to t of f prime of xs1 dws. And remember that x01 is just w0 and w, it was Brownian motion, so this is 0. So basically this is f of 0. No, so here our SDE, so now we can write everything in the form of this stochastic differential equation. The first coordinate xt1 can be just written as the integral from 0 to t of dws, which is basically wt. And xt2, given what we just wrote in the previous line, will be f of 0 plus 1/2 of the integral from 0 to t of f double prime of xs1 ds plus integral from 0 to t of f prime of xs1 dws. Now we are now in a place to apply our definition of intervention to this SDE. Now let's do this intervention. xt1 is zeta. Then xt2 just becomes f of 0 plus 1/2 of the integral from 0 to t of f double prime of zeta ds plus integral from 0 to t of f prime of zeta dws, which after simplifying will be f of 0 plus 1/2 of t f double prime plus wt f prime of sigma. And remember what we were expecting was this, which is the most natural thing. So this model does not work in this way.
So, but in the SD itself, on the second line, does xt2 actually equals to f of x?
Yes.
It's just a different way of
Yes.
writing it.
Just to be able to get to our setting. Mhm. So the two examples that were given. Okay, so that's about the mathematical definitions. Now we want to see how, so in the next section, we want to see how they relate to intervention in structural equation models. So basically, the bottom line is that the post-intervention SDE is the limit of a sequence of post-intervention SEMs. And now we will see how that happens. So first, just to make sure we are on the same page, a quick definition of a structural equation models. So a structural equation model, according to the setting of this paper, consists of 3 components. First, 2 families of random variables, a family xi, which is called the primary, the family of the primary variables, the family ui, which is called the noise random variables. So these are these 2 families. Then we have the directed acyclic graph G on a node set which we call V. and then a set of functional relationships as follows. So each xi will be considered to be a function fi of its parents and the noise. Now, just one thing to note here is that usually in the textbooks, when they define structural equation models, they assume that these noise variables are independent. And that is the assumption that later leads to the fact that an SCM is Markov to its graph, which it has some meaning. But here we don't need that property of Markovness, so let's just forget about it. And as a result, we will also not assume that the noise variables are independent. So it's a bit different from the usual definition that we might have seen. Now, how do we define interventions on SCMs? So let's see that. So let's say that we want to intervene on a subset of variables, not necessarily one of them. And that's how we do it. So let's say that we want to intervene on a subset A of all the variables. For each vertex in this subset A, define this I of A, which is the new parent set of this vertex I after intervention. So it will be a subset of V minus A. Now, we want to define this new structural equation model after intervention. In this model, remember, each structural equation model had three components. The first one was the variables, which we still have, the noise variables and the primary variables. The second one was the graph. So here, the new graph, G prime, is obtained from G by replacing the parents of each vertex that we have intervened on with the new parent set. So that's how we define the new graph. And how do we define the new functions? So in the functional relationships, we basically substitute all occurrences of xi for every I in A on the right-hand side of the equations with these new definitions of xi, which is zeta I of the new parents. So that's how we define intervention on SCMs. And the next step would be to somehow make a connection between intervention on SCMs and intervention on SDEs. But any questions so far?
I'm very puzzled about the two examples. One works and one doesn't. Anyways, we'll talk about the figure.
Yeah. Okay. Okay. So for the interpretation of this post-intervention SDEs, we first want to define something that the authors call signature of an SDE. It's different from the signature that we work on in our projects. It's just a graph of the SDE, and this is what it means. So let's say that this is our SDE. I just rewrote it here so we have it in front of our eyes. And the graph, which we call the signature of an SDE, the SDE, is a graph on the set of nodes, on the set of variables, which we have P of them. And the edge set, let's call it E, and this is how it's defined. So basically, K has an edge that points towards I, if and only if there exists some J such that A, I, J depends on the kth coordinate. So what it's saying informally is that there is an edge from K to I if xk appears on the right-hand side of the equation corresponding to xi, which is where it says one of the aij's depends on the kth coordinate. That's the definition of the signature. Okay, now it's time for us to define the SCM corresponding to a given SDE. So this is how they define it. Let's say that we fix a time point t and a time step delta such that t over delta is a natural number. Let's define n to be t over delta, so the number of time steps, and tk to be k times delta. So tk will be the kth time point. Now the SCM, which they call the Euler SCM, over this interval 0 to t with a step size delta corresponding to our SDE will be defined as follows. Again, we have an SCM. We want to define an SCM. We should define all the components. So the first component was the primary variables. Here, the primary variables will be x at all the time points tk for all i's. So I is just shows the coordinate of x that we're talking about. So it goes from 1 to p, and tk moves between the different time points. So k goes from 0 to. So this is the set of our primary variables. So we can say that we have p times n plus 1 of them. Now our noise variables here are, so the noise variables corresponding to xtki is ztk minus ztk minus 1. Okay, so two things here that might be different from the original definition of SCMs that we might have in mind, but is consistent with how they define SCMs here, which is a little bit different. So first, this is a d-dimensional vector, not one-dimensional. xtki is one-dimensional, but its noise is d-dimensional. And the second thing is that at a specific time point tk, for all the coordinates I from 1 to p, the noise is the same. So we can't say that the noise variables are independent of each other. And that's what they mentioned before. Because we don't want to use the Markovness of the SCM with respect to its graph, it's okay. We don't assume that the noise variables are independent in this setting for SCMs. So that's that. And so then the functional relationships are as follows. So xtki will be xtk minus 1i plus this, the sum over j from 1 to t of aij xtk minus 1 times ztk, the jth coordinate, minus ztk minus 1 jth coordinate. So this is kind of an approximation of the original SDEY, because if you take this to the other side, that's the difference of the ith coordinates between the two time points. And then, so this might be an approximation of dx on one hand, dxi, and on the other hand, we will have approximately aij of xt, and this is a representation maybe for dz at t. So that's why it's kind of natural to define the SCM corresponding to an SD in this way. And then the last component of an SCM should be its graph. So here our DAG is some graph G, where the nodes are all the primary variables as expected. So the nodes are indexed by 0 to n, the product of 0 to n and 1 to p. And the edges are defined as follows. So I1, J1 has an edge to I2, J2, if and only if first the time step, the second time step is exactly one more than the first one. And the reason is that in this equation here, for xtki, whatever comes on the right-hand side is something in the previous time point, tk minus 1. So the time points should have such a relationship here. And then J1 should be either equal to J2. So J1 and J2 show the coordinate number. So as you can see, xi in the previous time step is always on the right-hand side of the equation corresponding to xi tk. So that's why if J1 is equal to J2, we get an edge. Also, if J1, J2 is an edge in the signature of the ST. Yes.
Are you still sharing?
Yeah, yes.
No, you're not. Oh, yeah, you are.
Okay, so I should just go
Let
to
me
the.
just make this focus. Sorry.
Thank you.
Just a quick question.
Mhm.
The red face that you just write doesn't have any potential. You said that it's somehow an SDE,
Yes.
the approximation of SDE, but it doesn't have any potential times dt. That's because we have intervention here.
So here we haven't done an intervention yet. So this is basically the original SDE that we had. So this is our original model. Now corresponding to this, we want to define an SCM. I was saying that because this is how the SDE is written. This is the blue one is just the natural way of getting an SCM out of this. So getting rid of these D's, basically. You want to get rid of these differentials. And so instead of differential, instead of D of xi, as a representation or approximation for that, we just write xi at tk minus xi at tk minus 1.
So just to recap, this SDE that we have doesn't have potential. Potential times dt.
It's just the.
Well, it has dzt, but this zt might contain some t in it because zt is like a d-dimensional vector. So in some cases, like one of the examples I showed before, zt can possibly be t, and then, for example, a vector of Brownian motion.
Encoded the deterministic change and the random
Exactly.
change
Exactly. Yes. Yeah. So yeah, about the graph, I was just saying that for the second coordinates, J1 or J2 should either be equal, or there should be an edge from J1 or J2 in the signature of the original SDE, which we are showing with star. Which means that J2 should appear on the right-hand side of the equation of xtki. So just for an example, let's say that this is the signature of the SDE. So we have an edge from 1 to itself, an edge from 1 to 2, and then an edge from 3 to 2. Now, if you want to draw the graph of the corresponding SCM, okay, so for each time step, for each time point, we first consider all the coordinates, x1 up through x3. So this just continues until the last time point. And then, so for each time step, we have an edge from any coordinate to the same coordinate in the next time step, hence this horizontal edges. And then if we have an edge from 1 to 2 in the signature, we will have an edge from 1 in each time step to 2 in the next time step, hence these edges here. And then because of the edge 3 to 2 here, we have these edges here. And so this guy is our graph of the SCM. They have just added this noise vectors here too, which we don't usually add in the graph, but they've just added it, and well, they have edges to all of the primary variables. And it's clear, I guess. So any questions? Yes.
So the self edge on 1 doesn't do anything for the graph?
No, because we always have an edge from 1 at each time step to the next time step. So it basically doesn't do anything. Okay. So now the first result here. So I will present two results these two together show that the post-intervention SDE is the limit of some post-intervention SCMs. So two results. The first lemma says if A, remember A appeared here. If this A is a Lipschitz function, let's fix T to be a positive number, and let's consider this delta N to be a sequence of positive numbers such that their limit is 0, and for each n, T over delta N is a natural number. Now, for each n, or basically corresponding to each time step delta N, we can consider an SCM, right? Have that in mind. But then this says that there exists a solution to this equation. We'll get back to this later, but there exists a solution to this equation. And the important thing is that this solution satisfies that its variables are basically the primary variables in the corresponding Euler SCM. And these variables converge in some sense to the original, to the true solution of the SDE, which is xt. And this is how they converge. So the supremum of x, the absolute value of xt minus xtn, the supremum over all time points, converges in probability to 0. So this means that the solution to the SDE will be a limit of the solutions to the corresponding Euler SCMs. Now, just to work with this lemma a little bit, I'm going to give a sketch of the proof here. So what we want to say is that this differential equation here, this stochastic differential equation here, first has a unique solution. So let's rewrite this. So here, xcni will be x0 plus sigma j from 1 to d of the integral from 0 to t of this. Now here, this guy here is basically for each t, it's k delta n such that t is between k delta n and k plus 1 delta n. So we can split this integral onto several intervals as follows. So we can first do the integral from 0 to delta n. And on that interval, this function here will just be 0 for any t. And then we will have our dzsj. And then we can continue to write it for the interval delta n to 2 delta n. And we will have x delta n for any t from delta n to 2 delta n. Nu n of s will be delta n. And this just continues until the last possible time interval. Okay, so just looking at this differential equation when written this way, because now these are independent of s, one can clearly see that this has a solution and the solution is unique. So existence and uniqueness of the solution trivial, now that we wrote it this way. And now we want to say this xn, which is the solution to this differential equation, is also makes also the primary variables in the corresponding Euler SCM. So let's see. If we subtract x at, okay, so tk here was k delta n. So if we subtract x at the time point k minus 1 delta n, the ith coordinate, from same thing at the at the time point k delta n. This is what we get if you look at this guy. So everything here cancels out except for this. The integral on the interval k minus 1 delta n to k delta n of a ij x at k minus 1 delta n and then dzsj. And this will be equal to this. So if we just take the integral, we'll get aij at x k minus 1 delta n. And then the integral of dzsj will be z at the upper bound minus z at the lower bound. So k delta n j minus k minus 1 delta n j. And if you compare this equation with the Euler SCM that we defined corresponding to our original SDE, that's exactly that functional relationship that we defined for that SCM. So that's why we say the solutions to this SCM make the primary variables for the corresponding Euler SCM. So I basically showed the easier parts of this theorem. So I showed that the solution exists and is unique. I showed that the solution satisfies these variables are the primary variables in the SCM. I didn't prove this, the convergence, but it immediately results from a theorem in another reference, but I didn't show it here. Okay, so any questions so far about this lemma? Okay, so the other lemma says that again, if you have the same setting, so t is a positive number, delta is a positive number such that t over delta is a natural number. Now it's the time to do the intervention. So let's say that we want to intervene on the mth coordinate, and we want to set the mth coordinate to be some function zeta of the other coordinates. Then that's what we get. So if we first find the SCM corresponding to the SDE, and then do the intervention, we get the same thing as if we first found the corresponding SCM and then did the intervention on the SCM. So the order of these operations don't matter. We can first find the SCM, then take the intervention, or we can first find the intervention on the SDE and then find its corresponding SCM. That's what this lemma is saying. So this is what this lemma is saying. The other lemma was saying that the SCMs corresponding, the solutions to the SCMs corresponding to an SDE converge to the solution of the SDE. So combining the results of these two lemmas, we get that this diagram here commutes, meaning that we have this sequence of Euler SCMs corresponding to the observational SDE that converge to the observational SDE. We can then intervene on this observational SDE and get the post-intervention SDE. One other way to get to this point is to start from this sequence of Euler SCMs, do the intervention on these SCMs. We then again get a sequence of post-intervention SCMs, which by the first lemma, again converge to the post-intervention SDE. So that's basically the summary of this part that this diagram here commutes. So this basically, according to the authors, doesn't get anything in terms of why this notion, like how this notion is a good notion for causality. They say that the only reason they added this section was to say how this notion relates to the already existing and agreed upon notions of interventions for non-temporal models. So yeah, that's that. Any questions so far? Okay. So the last result that I want to talk about is an identifiability result about this post-intervention distributions. If basically we want to ask if post-intervention distributions are identifiable from observational distributions. And I think the result is a little bit technical. There are several lemmas that result in the main theorem, and also even just to state the theorem, I should give some definitions which might not make sense if you are not looking at the proof, but I will anyway give them just to be able to state that theorem. So here I should define a Levy triplet. So first, a Levy measure. So a Levy measure on RD is a measure, let's call it nu, such that first nu of 0 is 0. So the measure that is assigned to 0 is the 0 measure. And that this function, which takes x to the minimum of 1 and the norm of x squared is nu integrable. So that's the definition of the Levy measure. Now, what is a Levy triplet? They call a triplet a d-dimensional Levy triplet if it consists of alpha c nu, where alpha is just an element of RD, C is a positive semi-definite matrix of size D times D, and nu is a Levy measure. Why are these Levy triplets important? Because of the following theorem. So for any bounded neighborhood G of 0 in RD, and for any d-dimensional Levy process, we have the following. We have that there exists a Levy triplet alpha CV such that we can get the following expected value with this formula. So I think that this might not make very much sense if we are not looking at the proofs, but anyway. And so if we can get this expected value with this formula, this means that this triplet, alpha CV, uniquely determines the distribution of X. And the converse is also true. So for any bounded neighborhood D of 0 in RD and any Levy triplet alpha CV, there is a Levy process whose corresponding Levy triplet is alpha CV. And so we call this alpha CV, sorry, alpha C nu, the D characteristic of the characteristic triplet of X. Maybe just to summarize, for any Levy process X, there is this triplet that uniquely determines the distribution of X, and we call that the D characteristic triplet of X. Now, this triplet allows us to define something called the generator of an SDE, which is a linear operator on the set of continuously twice differentiable functions. And that's how it is defined. So I just show you the definition quickly. So again, let D be a bounded neighborhood of 0 in RD. Consider the SDE that we always have. And again, let Z be a d-dimensional Levy process. So this result of identifiability is restricted to Levy processes here. And consider this Levy process to have the D characteristic triplet alpha CV. And then A is just the function that appears in the SDE. Now, the generator A of the SDE is defined as follows. So the generator takes a function, F, and outputs another function, which is defined as follows. Now, the thing is this theorem that follows from this. So if we have two SDEs with variables xti and x tilde ti, with two different functions, a and a tilde, and even the dimension of their Levy process, so the random part can be different, can be d and d tilde. So as long as this z and z tilde are both Levy processes, and as long as this function a is Lipschitz, and the intervention function that we will use later, zeta, is also Lipschitz, then if the two SDEs have the same generator and their initial values, so these two, have the same distributions, then they prove that their post-intervention distributions will also be the same. So basically, the summary is that in SDEs with under some Lipschitz conditions, and with the Levy process as the driving semi-martingale, the post-intervention distribution is identifiable from the generators. It's just one thing that I was confused about. So in their theorem, they just say that this function A should be Lipschitz here. They don't say that A tilde should be Lipschitz. But when I looked at the proof, it seems that they also use the Lipschitzness of A tilde. So I think it's just a typo or something, but I just wrote it here as they wrote it in the paper. So yes, I guess yes, it's 10:12, so I can stop here. Thank you.
So it's identifiable from the generators, but does that mean it's identifiable? I guess if you know this from observation.
So if you, yes, if in many cases when you know the observational distributions, that means the same generators, and then that means the same post-intervention distribution, which is one of the examples. Yes, sure. Yeah, this is this guy A. And so there was this example that I wanted to just show you if we had time, which we don't have now, but the summary of the example is that they give these two SDs that have the same observational distributions, and they have the same generators, and as a result, they have the same post-intervention distributions, but their signatures are different. So the graphs corresponding to the SDEs are different. And then from there, they say, so we believe that signatures shouldn't be our way for inferring causality, because there might be two, because signatures are not identifiable from observational distributions, while post-intervention distributions are identifiable. So they say, okay, so we believe we should look at post-intervention distributions instead. And they also mentioned that we think this instance where where signatures are not identifiable should be atypical, so they shouldn't happen in many cases, but they don't have any specific results about that. They just mentioned this sentence in basically 2 parts of the paper, and that's it.
Do you think that people have studied this, like in just the SDE literature, or what happens if it's not random?
I don't know.
Basically, you have,
So if
different ways of finding the SDE, but then you get the same solution.
we don't get the same solution, but we get the same distribution for the post-intervention solution.
Yeah.
Yes, exactly. So this example that I wanted to show was exactly that. The SDEs are different, so the solutions, I'm not sure if the solution, no, actually in that example, the solutions are also the same. but which means that their observational distribution is also the same. But yeah, the STs are different, and like the functions A in the STs are different, which gives different signatures. But then they have to find the same post-intervention distribution.
That's very cool.
Mhm.
So when I was skimming the paper, I kind of highlighted the last paragraph of the second page, which says like, in classical DAG-based models and causality, such as whatever, neither the DAG nor the effect of interventions can be identified from the observational distribution. Theorem 513 essentially shows that for levy and STE models, the effect of interventions can be uniquely identified from the observational distribution.
Yes.
So that seems like a major result, but I checked, the citations. It's a lot. It's like, but it's less than 50.
Yeah.
So I'm wondering what's going on here. Like, is it actually insanely important, or is there some caveats that I'm missing?
But one thing that we know for sure is that this setting is not even applicable to some models, right? Like the one that we showed. So
Right.
if we don't even have like the initial assumption that this is our setting, what can we do with identifiability? So maybe that's one.
Wait, which result?
What?
Which result?
It's just the last paragraph of page 2. It's just kind of nice summary. So, like Elena was asking before, I didn't understand the difference between the two examples of when it worked and when it didn't. What was different about them?
I think it was just, so my understanding is in the first example, well, it comes from a real world setting, first of all, and it is also important how we choose the model, right? We initially wrote the model using an SDE, and then maybe that was something that helped, because they also say that this model can be written, like people have used other different models for these reactions. So I think the choice of our model was something important here, because in the other example, we initially chose the model to be this. So we didn't use any SDEs or anything, and we just had to change the appearance of this model to have it look like ours, and then apply our definition. So maybe like I'd say the choice of model was something that didn't work in the second one. And well, maybe there are settings where this is the better choice of model to start with.
Didn't the Ito formula miss?
No, so it's not the Ito's formulas, it's that so I think it's that in this definition, like in the definition of post-intervention STEs, we are not allowed to substitute integrators with something. So we are not allowed to substitute this WT with, so here, we are not allowed to substitute WT with the constant. Because if we were originally able to do that, then everything like here would be 0, and we get just xt2 is f of the constant. But in their definition, they don't allow for substituting for the integrators, and that's something that messes up, because they also mentioned that that is a possible path to take, but it just makes things complicated, and we won't investigate it any further. So.
Can you scroll to the SEM part?
Yes.
Down a bit more, and to the graph itself. Yeah. So in this graph, it almost seems like there's, so they put the noise in the graph, but in a way, it's not noise anymore, because it's like going to all of them. It's almost like one unobserved confounded, right?
Yes, but yeah, But I guess they consider it as noise because they don't care about whether or not their noises are independent.
Yeah, because to me, it almost seems like they're like saying, oh, look, we're getting rid of this assumption
Yeah.
about independent noise, but then they're assuming that the same things get applied to all variables,
Mhm.
which is almost stronger. I don't know, but
Yeah, it's like taking away some part of the definition of SCMs, but then they argue that this is only important because we want to say SCMs are Markov to their graphs, and we are not using that here. But yes, if I mean, I think if we want to relate our notion to the pre-existing notion, maybe we should just use all the definition and not take away part of it. So that's something they do.
Yeah, I'm curious about the citations, but maybe we should also look at the other works by the same group.
Mhm.
I wonder if they rely on this or they just
Mhm.
something else. Should we think partisan?